Like in my previous video for approximations of the exponential function of the Taylor series, similarly I would like to see if or how can we approximate the natural logarithm function with this Taylor formula. So here you can see the original representation of the formula, summing all these terms with nth order derivatives plus the remainder term, which is a varying point between a and x. Here are the derivatives, and this is the general form of derivative of the nth order derivative, which if you plug in this general form you will get this final result with this intermediate C point. After a little bit simplification and using this logarithm subtraction rule, which can be written in this form, we can get this final result where I substituted x over a with this capital X. And the corresponding midpoint is between 1 and 1 over x, which means that the remainder term, plugging back this value, it's varying between this border or this part and this part. If you analyze these values, x also 1 over x, that means that if x is greater than 2, like 3 for example, we will get here minus 2 to the power of n, which in normal case n tends to infinity, means that we get an infinity or infinitely large value. So the remainder term is not something we can use to approximate normally. Seems that will not help us too much. If n approaches to infinity, the remainder term cannot be predicted how much, or if it will tends to 0. It's not 0. In this case, the remainder term is a very great, or it's a very big value, which ruining our expectations. So this is just for demonstration that there exists many functions with specific values, or how to say that in this Taylor formula, if this power term is not between minus 1 and 1, then the approximation might be very wrong. So usually this Taylor formula is useful if this power term is less than 1 or greater than between minus 1 and 1. Let's see the software. What's doing here? I wanted to compute logarithm of 2, which means that this should be the original value of logarithm of 2, and this is the polynomial approximation by the Taylor polynomial, the series, that sum, this sum, which is with negative sign, but 1 minus x to some powers. So not so good. I used 20 terms to approximate, and here you can see the same thing, but adding the correction term, which is a remainder term, which is not what is the general Lagrange mean value theorems or Lagrange remainder, but my specific remainders, what I'm usually computed, like in the exponential functions video. I had 3 kinds of the remainder terms because This is more accurate. The third one is the best. This is a midware, and this is a general term, which can be used in all the time or any time. Can use it. It's a very good results anyway. The difference between these remainders can be seen here. This is the original remainder term, which means that I just subtracted from logarithm of 2 the polynomial, and this would be the original remainder. And here are the approximated remainders. So the general term is with 2 decimal points, where 2 decimal places is good. The second remainder term is much better. As you can see, it's 6 decimal places. Approximates the remainder term. And the second one tries to be somehow better. It's 1 decimal places more than the first one. So I think the single value which this Taylor formula is good for approximation of the logarithm is the number of 2, because here if you plug in 3, logarithm of 3, this should be the original value, but the polynomial will compute a very wrong value. It's a 34,000 with negative sign, some kind of strange. And if I'm growing the steps, it's worst. It's 10 to the power of 27. It's insane. So in normal conditions you cannot use the Taylor formula for greater values. The only thing what can be done here, be using the trick that we used also here, the logarithm of x over a is a difference between logarithm of x and logarithm of a. So if you are using logarithm of 1 over x here, like 1 over 3, then we should get the value of logarithm of 1 minus logarithm of 3, and because logarithm of 1 is 0, remains minus logarithm of 3. So we would get logarithm of 3 but a negative sign. And because x is less than 1, this term to the exponent is not growing, will be an acceptable value between 1 or less than 1. So it might be useful. Let's see what will happen if I'm using 1 over 3. So we get the same result but with negative sign. And now the polynomial approximation seems very good. Look at here, how many decimal places. So even the Taylor series can be useful in this case, if I'm using 1 over x as the plug-in value. And if you're also using and adding the correction term like my remainder, you will get some extra decimal places, like in this case just 1. But if you can grow, or you are growing to so much, then it might be better. Like the original polynomial is until here is approximates, and with the remainder term you will get 3 decimal places more. As you can 647. And the polynomial only until here it was approximated. So this approach would be the single which can be useful for approximation, but anyway this method cannot be used as a computer algorithm because it's too slow. Just computing 200 terms to get 10 decimal places, and I forgot to say that it's just free. The problem is starting when you are using a big number here like 377 or some bigger numbers. You can see even the polynomials get worse again. It not even 1 decimal point is computed. You need more steps, like 1,000 steps in this case, to get a single decimal point approximation results with the Taylor polynomial 5.9. And with the remainder term you can get one additional decimal point. So this would be a demonstration that not in all the cases you can use a Taylor approximation.